Off the coast of North America, there's this fault line, 1,000 kilometers long, just sitting there. But it's not sleeping. It's locked up, totally stuck, holding back centuries of tectonic pressure. That's not me being dramatic. It's the actual physical state of the Cascadia Subduction Zone right now. For more than 300 years, it's been building up force, saving it all for one massive, catastrophic release. When it finally lets go, the earthquake won't be a magnitude 7 or even a modest magnitude 8. Oh no, it'll be a full 9.0 megathrust event. The shaking won't last for 30 seconds. We're talking 5 to 7 continuous minutes. And then the real clock starts ticking. For anyone on the coast, all the way from Northern California to Vancouver Island, the second the shaking stops, they'll have maybe 10 minutes, tops, before a wall of water up to 100 feet high crashes in to wipe out the shoreline. This isn't some crazy prediction or a worst-case scenario. This is what's happened before, written in dead trees and old Japanese records. And what we've learned in just the last 2 years? It suggests even that timeline, even that kind of disaster, might not be the absolute worst of it. The true story goes way deeper, and honestly, it's much more dangerous. To get a handle on this whole threat, you first need to understand what the Cascadia Subduction Zone isn't. It's not the San Andreas. That fault, the one that gives California its earthquake anxiety, is a strike-slip fault. It's two plates grinding past each other horizontally. Yeah, it makes violent, damaging quakes, but there's a physical limit. Usually, it caps out around an 8.2 magnitude. Cascadia is a whole different beast. It's a subduction zone. Here, the entire Juan de Fuca oceanic plate is sliding right underneath the much bigger North American continental plate. This is happening right now, 70 to 100 miles offshore. But the plates aren't sliding smoothly. They're stuck, jammed together by friction across a 600-mile stretch. For 3 centuries, the North American plate has been bulging upwards and compressing to the east, kind of like a giant spring getting coiled tighter and tighter. When that spring finally snaps, the resulting 9.0 earthquake will release about 30 times more energy than an 8.0. That's just an insane amount of force. And unlike California's noisy faults, which constantly let off steam with small, rattling tremors, Cascadia is unnervingly quiet. It almost never has minor earthquakes. For decades, scientists actually confused this silence with safety. They figured the Pacific Northwest was just immune to big seismic hazards. They were really wrong. The silence isn't safety at all. The silence is the entire problem. It means the fault is 100% locked. It's not releasing any pressure. It's just storing every single ounce of tectonic stress for one colossal event. Official government estimates put the chance of that event happening in the next 50 years at somewhere between 10 and 15%. That number is for a full margin rupture, the real M90 big one. You might have heard a different number, a much higher one, like a 37% chance of a major quake in the next 50 years. That number is true too, but it's for something different. That's the chance of a partial rupture, still a devastating magnitude 7.1 or higher quake, but one that only hits the southern part of the fault. The media messes this up all the time. Seismologists don't. To them, a 10 to 15% chance of the entire 600-mile line unzipping at once is practically a geological certainty on a human timescale. The only real questions are when, and just how awful the new science says it will be. For most of the 20th century, the proof of this coming disaster wasn't just hidden, it was completely unknown. The scientists believed the Pacific Northwest was quiet. They thought the plates were moving, sure, but they were sliding past each other without generating the kind of crazy earthquakes you see in places like Chile or Japan. The region's Native American tribes, though, had these oral traditions full of stories about epic battles between thunderbird and whale that actually shook the land and sent the sea rushing in. But people just dismissed those as myths, folklore. Then, on May 18, 1980, Mount St. Helens erupted. That blast was a huge wake-up call, proving beyond a doubt that there was massive tectonic energy in the region. The eruption made a new generation of geologists start looking a lot closer. One of them was a scientist with the USGS named Brian Atwater. This was in the mid-1980s, and he wasn't even looking for earthquakes. He was studying coastal geology. He started digging around in the tidal flats and salt marshes along the Washington coast, places like the Copalis River and Nia Bay. What he found there totally rewrote the history of a whole continent. He found these ghost forests, these groves of huge dead red cedar trees just standing silently in the tidal muck, killed centuries ago. When he dug down, he saw their root systems were still buried in an old soil layer. Right on top of that soil was a distinct thick layer of sand, the kind that gets deposited not by a river, but by the ocean. And above that, a layer of tidal mud. The story these layers told was crystal clear. At some point, the coastal land these trees grew on must have suddenly and violently dropped by as much as 6 feet. The forest floor just plunged below sea level, and the ocean flooded the trees with salt water, killing them instantly. A massive tsunami must have crashed in moments later, burying the dead forest in a blanket of sand. It was the physical fingerprint of a gigantic earthquake and tsunami. But when did it happen? Atwater and other scientists used tree ring dating to figure it out. All the ghost forest cedars died at the same time, sometime between late summer 1699 and spring 1700. The rings showed they were healthy one season and dead the next. The final piece of the puzzle came from literally halfway across the world. Across the Pacific, Japanese historians had kept incredibly precise records for centuries. Those records documented this strange and devastating event. On the night of January 26, 1700, a massive tsunami hit the coast of Japan. It came out of nowhere. There was no local earthquake, no shaking, nothing to warn them of the coming wave. It destroyed seaside villages and flooded fields. The bewildered officials wrote it down as an orphan tsunami because its parent earthquake just couldn't be found. When scientists in the 1990s lined up the timelines, the mystery was solved. The death date of Brian Atwater's ghost trees in Washington matched perfectly with the arrival of Japan's orphan tsunami. The earthquake could only have happened on the evening of January 26, 1700, local time in the Pacific Northwest. Calculating the tsunami's travel time across the ocean, scientists even pinpointed the moment of the quake, around 9 p.m. Those native legends weren't myths after all. They were eyewitness accounts. The Cascadia Subduction Zone wasn't quiet. It was waiting, and the clock on its recurrence interval had been ticking for over 300 years. All of this was known. It was established science, scary enough to kick off a wave of public awareness, largely thanks to a 2015 article in The New Yorker. Catherine Schultz's piece, The Really Big One, took this obscure geological threat and made it a terrifyingly mainstream reality. After her article, people really started grappling with what was coming. But the science didn't just stop there. What we've learned since then, just in the last 2 years, has made the picture even clearer. And much, much more alarming. Imagine the moment it starts. Not a sudden jolt, but a deep, low rumble that quickly becomes uncontrollably violent. For the next 5 to 7 minutes, the ground won't stop moving. That amount of time is nearly impossible for a human mind to really grasp. A typical California earthquake is over in 15 to 30 seconds. This is 10 to 20 times longer. Long enough for soil liquefaction to take hold in the reclaimed tidal flats and river valleys, where much of Seattle and Portland are built. The solid ground under buildings, bridges, and buried pipelines will temporarily act like a liquid. Structures on this artificial fill will sink. Gas lines will snap. Water mains will shatter. The cities will start ripping themselves apart from below even before the shaking stops. As the ground shakes, the land itself moves. The whole continental shelf, a massive slab of earth the size of a state, instantly drops by up to 6 feet as that tectonic spring uncoils. At the same time, it rebounds westward, lurching 30 to 100 feet in mere minutes. This colossal movement of the seafloor is what creates the tsunami. It's not like a wave driven by wind. It's the entire ocean rising all at once. For those on the coast, the clock literally starts now. 10 minutes. Maybe 15. 20 if you're really lucky. That's the time between the end of that violent 7-minute earthquake and the arrival of the first wave. A churning wall of water, potentially 100 feet high in some spots, moving at the speed of a jet airliner across the open ocean. slowing down as it gets to the coast and piling up on itself. It won't be some nice, clean surfing wave. It will be a churning mess of debris, logs, cars, and pieces of buildings, scouring the land clean. This catastrophic scenario is why we got the most famous quote in American disaster planning. Kenneth Murphy, a former regional director for FEMA, just flat out said what the official federal position was. Our operating assumption is that everything west of Interstate 5 will be toast. That line often gets taken literally, making people picture total annihilation. The reality is more complicated, and in some ways, even more terrifying. It doesn't mean every single person west of I-5 will die. The casualty projections, grim as they are still a fraction of the total population. What toast means is the complete and instant collapse of modern society in that area. The power grid will be gone. Water and sewer systems will be shattered. The transportation network won't exist anymore. Every major bridge will be a candidate for collapse. Every overpass, a potential roadblock. There will be no way to drive in or out. No way to call for help. The entire region, home to millions of people, will become a bunch of isolated islands, cut off from the rest of the world, with no power, no running water, and no way to move around. FEMA's assumption is that for weeks, possibly months, people in the inundation and liquefaction zones will be totally on their own. That was the basic understanding. A disaster almost beyond imagining, but one we thought we'd finally wrapped our heads around. Then, new information started coming in. On June 7th, 2024, a team of scientists led by Suzanne Carbett of Columbia University published a study that completely changed how we see the fault. For decades, geologists had been working with a low-res, almost blurry idea of Cascadia's underwater structure. Using a research vessel called the MG Langseth, Carbott's team used advanced acoustic imaging to create the first ever high-resolution sub-seafloor map of the entire subduction zone. Carbott explained the breakthrough with a great analogy. It's kind of like you had Coke bottles over your eyes, and they've been removed. And you've got the proper prescription. Now you can see where the fault zone is. And what they saw was an immediate worry. The fault wasn't one continuous, smooth plane like they thought. It was clearly split into at least 4 distinct segments, each with its own quirks. The segment that really stood out was the one right off the coast of Washington. It was flatter, smoother, and shallower than the others. In geology, smoother isn't better. A smoother, flatter fault segment means a bigger contact area between the two tectonic plates. More surface area means more friction, more places for the plates to get stuck together. More being stuck means more stress can build up. More stress means a more violent release. The single segment with the highest potential for devastating shaking was now identified, mapped, and it's sitting right off the coast of one of the most populated areas of the Pacific Northwest. The picture of what would happen was getting sharper. And then, the projection of who it would happen to got much, much worse. In June of 2026, a new study funded by NOAA and done by the Washington Emergency Management Division gave a stunning new assessment of the human cost. For years, the official FEMA models had predicted fatalities for a full rupture scenario in the range of 14 to 25,000 people. Horrific, sure, but a number planners had been working with for a decade. The new Washington MD report concluded that these federal models understated the risk considerably. Their state-level analysis, using more specific data on local topography and infrastructure, found that the actual number of casualties in the coastal inundation zone would be staggering in comparison. The reason was brutally simple: for tens of thousands of people. There's just no high ground to get to. The low-lying coastal plains of Washington offer very little natural elevation. The promised network of vertical evacuation towers, structures built to let people climb above the tsunami's crest, has been slow to get built. In just the 10 to 20 minutes available, reaching safety will be physically impossible for many. The old estimates were abstract models. The new ones are a grim calculation based on geography and time, 2 numbers that just don't add up to survival. And just as the world was trying to process all this, another discovery hit. This one changed the very definition of what the worst-case scenario even meant. For years, the big one was Cascadia. That was the ultimate disaster. But Chris Goldfinger, a paleoseismologist at Oregon State University who spent his career studying Cascadia's history, presented new research in mid-2026 that suggested something far worse. His team had been analyzing sediment cores from the ocean floor, looking at the layers of underwater landslides triggered by past earthquakes. The data suggested a partial synchronization between the Cascadia Subduction Zone and the San Andreas Fault to the south. Historically, it looked like a huge rupture on one fault could be followed pretty quickly by a major rupture on the other. A Cascadia Megaquake could potentially trigger a massive earthquake on the San Andreas. Or the other way around. The implications of this are almost too big to even think about. Not one disaster zone, but two. A catastrophe stretching all the way from Vancouver Island down to Southern California. The two most feared seismic zones on the continent, acting together. In Goldfinger's own chilling words, we're used to hearing the big one, Cascadia. Being this catastrophic huge thing, it turns out it's not the worst case scenario. Suddenly, the event we'd been bracing ourselves for, the M9.0 that would redefine the West Coast, was possibly just the opening act. The sheer scale of this threat can feel totally paralyzing. But steps are being taken. In 2023, the National Science Foundation set up the Cascadia Region Earthquake Science Center, or CRESCENT, with a $15 million grant. It's supposed to be the nation's top research spot for understanding subduction zone hazards. State agencies like the Oregon Department of Emergency Management and the Washington Emergency Management Division are running public education campaigns, doing drills, and working with local communities on preparedness plans. Cities are slowly retrofitting bridges, hospitals, and schools. The government and science machine is working. Reports are being written. Budgets are being approved. Plans are being made. But here's what no report, budget, or plan can change: the math. At its heart, this crisis is a math problem with numbers on a geological scale. It's a 1,000-kilometer fault line holding back 326 years of stress versus a 15-minute evacuation window. It's a 100-foot tsunami versus coastal communities built mere feet above sea level. It's millions of people living in a region where the vital stuff, its bridges, its power grid, its water supply, was built with no understanding of the forces that will eventually hit it. The government can pass bills, scientists can make better models, but they can't make the Juan de Fuca plate stop subducting. They can't add more time to the tsunami countdown. They can't hold back the Pacific Ocean. The issue really comes down to scale and time. Our human systems for dealing with things work on timelines of years, budgets, and political cycles. The Cascadia Subduction Zone works on a geologic timeline driven by the unstoppable physics of a moving planet. The energy building up offshore doesn't care about our preparedness drills. It doesn't recognize our disaster declarations. It just accumulates, day after day, year after year. The gap is huge. We plan in human terms for an event that's geological in nature. We're trying to build a lifeboat while floating on top of a volcano that's already rumbling. Every new scientific finding, from Carbot's fault maps to Goldfinger's double threat, just makes that gap wider between what we know is coming and what we can actually do about it. The numbers aren't getting better. The scenarios aren't becoming less severe. They're all moving in one direction, toward a rupture that isn't a question of if, but a certainty of when. Look again at those ghost forests on the Washington coast. Those silent, gray cedar trunks aren't just remnants of the past. They're basically a preview of the future. They're a physical record of the last time this fault broke. They show us what the land does, what the sea does. They're a warning, carved in wood, from the year 1700. The samurai in Japan who wrote down the arrival of a wave with no earthquake were left with a mystery they could never solve. We don't have that excuse. We know where it comes from. We've mapped the fault. We've dated its last rupture to the exact day. We've calculated the height of the wave and how long the shaking will last. We have the data. We have the models. We know what's coming. That silence off the coast isn't peaceful. It's the sound of a spring being wound tighter. Every day that passes without a major earthquake isn't a day of rest. It's another day of pressure building up in the system. Another 24 hours of energy stored, just waiting to be set free. The West Coast is living on borrowed time, courtesy of a fault line whose patience is running out. The ground under millions of people doesn't have a hypothetical risk. It has an expiration date. We just don't know the year.